today's lesson. Hopefully you're still hungry from that grilled cheese sandwich we had last time. And in the last lesson you looked at the differences between, or tried to figure out how to deal with the limiting reactants problem. So if you had an equation where one of the two reactants ran out before the other one, how do we deal with that? Hopefully that made sense to you. We just dealt with it in a multimole ratio way. This particular little mini video here, we just go forward that one last step and take it to mass ratio. So that shouldn't be too hard for you, I hope, if you're awake. We'll see. Hopefully this will make sense to you as well. So in this one, what do we got going on? Remember we talked about our grilled cheese sandwich. We had 2 pieces of bread, 1 piece of cheese. Gave us one particular sandwich. And then we looked at what would happen, how we could figure out how many sandwiches we could make given a set number of pieces of bread and pieces of cheese. So what happens if we're not actually given a number of slices? I don't remember what it was in the last one, if we had 24 pieces of bread and 18 pieces of cheese, something like that. But what if you weren't given a number of slices? What if you're given masses instead? Because this is really more like what happens in chemistry. So what if we said you had 740 grams of bread and 738 grams of cheese? How many sandwiches could you make? A little bit harder because we don't know individuals. And we know that bread and cheese reacts on a slice-to-slice basis, not really a mass-to-mass basis. So we need one more piece of information, and that's that mass-to-slice conversion. Chemistry, we call it molar mass. But here's our mass-to-slice conversion at the bottom. I know from the package that 1 slice of bread weighs 37 grams, and 1 slice of cheese is 21 grams. So the next thing should be pretty straightforward. We need to figure out how many slices of bread, how many slices of cheese we have. So this is time for the diffractions, yeah. So we have some colors here. We have green was given to us in the problem. We have blue is the mass-to-mass conversions, yeah. And we have the ratios, yeah, from our balanced equation. Those are in red. So here we see at the top, we see the lovely one that goes on for the bread. So up here we were given 740 grams of bread. And we know that right here, there's our bread to mass ratio, 37 grams of bread, 1 slice. And then our last one was our 2-to-1 ratio, that 2 slices of bread is 1 sandwich. So overall, when we do the calculations and you get your calculator out, you'll find out that that's a total of 10 sandwiches that we can make from 740 grams of bread. Hopefully you can follow the cheese one on your own. But if we have 378 grams of cheese, I know that 21 grams is 1 slice, and then 1 slice of cheese is on 1 sandwich. Not my ultimate sandwich, but in this particular problem, there we go. And so for this one, when you do the math out, you find that you can make a total of 18 sandwiches. So there you go. We have to do that mass to slice, I guess, conversion first. And this is what's kind of interesting down here at the bottom. Whoa, can't draw straight with my fingers. Even though the bread weighed a lot more, I mean, we had twice as much bread, 740 grams. Even though the bread weighed more, it was still the limiting reactant for a number of different reasons, because of the, bread to slice mass ratio and because of our 2-to-1 ratio. So overall, we still have bread as being our limiting reactant because there's only 10 sandwiches that we can make from that. So now let's take a look at chemistry instead of sandwiches. I'd rather think about sandwiches too. But we don't use mass to slice conversions. We use mass to mole conversions. We call those molar mass. And here's our kind of classic reaction that we've used repeatedly, the Haber process. So if you have a problem like this, if you react together 125 grams of nitrogen gas and 250 grams of hydrogen, how much ammonia can be produced? So just like in our sandwich problem, we have to use a gram to quantity conversion. In this case, it's molar mass. And you'll have, I put on there for you, your molar masses of nitrogen gas, 28.02, and hydrogen gas, 2.016, in case you don't have a periodic table. So let's do our conversion. So here it is. Just like in our last Wunderfractions example, we started off with 125 grams of nitrogen gas. Nitrogen gas is 28 grams per mole. Again, it's N2. Nitrogen each weighs 14, so that's why it's 28. But nitrogen gas weighs 28 grams per mole, roughly. And in our balanced equation, it's 1 mole of nitrogen gives us 2 moles of ammonia. Again, 1 mole of nitrogen gives us 2 moles of ammonia. So there's our 2-to-1 ratio. And when we do that calculation out, we predict that we could make 8.92 moles of ammonia. We go through the same process with hydrogen gas. We start off with 250 grams of hydrogen gas. Hydrogen gas is about 2 grams per mole, again, because it's H2, so we have to add 1.008 times 2. And then now we have our mole-to-mole ratio here is 3 to 2. And again, that comes from the balanced equation up above, because our hydrogen's got a coefficient of 3 in front of it. So when you do this out, we could actually make 82.7, it's a lot, moles of ammonia. So we can tell by looking at this that nitrogen must be our limiting reactant. Again, why? Because nitrogen can make less, therefore it's the limiting one. We've got more than enough hydrogen. We can make tons of ammonia from the amount of hydrogen that we have, so it's our excess reactant. So again, we're going to take a look at this particular values where we got to go forward in our next step. Just looking at the nitrogen, because it's the lower number, we know we can make 8.92 moles of ammonia. But we're not done. We have one more conversion to do. In chemistry, we don't usually give our answers in numbers of moles, simply because that in a chemistry class or a industrial setting, something like that, I don't have a scale that weighs in moles. It's usually going to be in grams. So we have to do that one last step of converting our moles of ammonia that we got to grams of ammonia. I've got the molar mass written on there for you. It's about 17 grams per mole, 1 nitrogen plus 3 hydrogens. So there's our last little conversion right there, that if we take a look at how much it weighs, we realize that we could make about 152 grams of ammonia, and again 3 sig figs. So the next problem is your turn. Here's an equation up at the top. Aluminum reacts with chlorine gas to form aluminum chloride. According to the Fallon's balanced equation, I was nice, I gave it to you balanced. 2 aluminum atoms would react with 3 chloride molecules, chlorine molecules, to produce 2 aluminum chloride molecules, I guess. So here's our problem. 10 grams of aluminum are reacted with 35 grams of chlorine gas. What mass of aluminum chloride can be produced? So this is a good chance for you to click pause, go grab a pencil and paper. You probably want a calculator too. I put the molar masses down at the bottom. Didn't put units on them, lazy. But I put molar masses down at the bottom there for you. So the molar mass of aluminum is 26.98. The molar mass of chlorine, not chlorine gas, just chlorine atom, is 35.45. So go ahead, hit pause, scratch this one out, see if you can come up with a solution. When you're ready, hit play, and you'll see how I have it worked out on the next page for you. Okay, welcome back. Here you go. Here's our problem at the top again. Start with what we know. We have 10 grams of aluminum, so that's our first problem that we're working on right here. 10 grams of aluminum is converted right here. There is our molar mass step. 26.98 grams of aluminum is 1 mole. And then our last step right here is our mole to mole step. So we could figure out that 0.371 moles of aluminum chloride could be produced. Again, this 2 to 2 right here came from the fact that there's a 2 in our balanced equation for aluminum and a 2 in our balanced equation for aluminum chloride. So just looking at chlorine now, our problem said 35.0 grams of chlorine gas. There's our 35 right there. Next step, molar mass. I had to do a little trick in here. Molar mass of chlorine gas, Cl2, is not 35.5. It's 2 35.5s, so it's actually 70.9 is grams per mole. And then our last step is our mole to mole ratio. And again, we have a 3 to 2 ratio here because there's 3 chlorines give us 2 aluminum chlorides. So we always kind of go through the same step. We start with grams, we convert grams to moles, and then in the next step we convert moles of one to moles of something else. And here's our 2 answers. So if we just look at aluminum, we could get 0.371. If we just look at chlorine gas, we could get 0.329. This one is our lower number, so that's got to be the one that we want to take a look at for our next bit. That's our chlorine's our limiting reactant. So here's our next part. Last step, we take our lower number, and again, one more time, we convert grams, or sorry, in this case, moles to grams, because our last answer was in moles, and our final answer here is 43.9 if you look at 3 sig figs. How'd you do? Did you get it right? If not, you better ask me a question in the morning. Have a good weekend.